This is the video where naming starts to feel natural. Hey there, ninjas. In this video, we're going to work through a lot of worked examples of molecules with substituents. We're going to start fairly simple and work our way up to higher and higher ninja levels, until we get to some really complicated molecules by the end. You'll get to see examples of all of the rules and all of the sub-rules and all of the sub-sub-rules for naming molecules with simple substituents. This isn't a video about the IUPAC rules, but I do have a link to that video in the description below. In short, every IUPAC name can be broken into 5 parts. Not every molecule has stereochemistry. Some molecules may or may not have substituents, but every molecule needs a syllable for the parent hydrocarbon, the unsaturation, and the priority functional group. This video actually won't really get into priority functional groups very much. I have a separate video on that I'll link to below. In this video, we're really going to be focusing on the substituents. How do we find them? How do we name them? And how do we put them in the correct order in the IUPAC name? Let's start with a simple example. This is the simplest branched hydrocarbon that we can name in organic chemistry. Going back to our rules from our previous video, first we need to find the longest consecutive carbon chain of carbon atoms. This molecule has several 3-carbon chains. For this molecule, we could pick any one of them, but we'll pick the 3-carbon chain here linearly across the molecule. Then we number that molecule to give the highest priority functional group the lowest overall number. There is no priority functional group in this molecule, and whether we number right to left or left to right, the substituent will always be at carbon number 2, so we'll keep it simple and number left to right. The next step is to name the parent hydrocarbon. There are 3 carbons in the longest consecutive chain. The parent name for our 3-carbon hydrocarbon is propane. This molecule has no unsaturation or priority functional group, so the base name for this parent is really going to stay propane. The next step is to make a list of all the substituents and their locations in the molecule. This 3-carbon parent chain only has one substituent sprouting off of carbon 2. The substituent are only the carbons that sprout off of the parent hydrocarbon. The substituent does not include the carbon containing the parent hydrocarbon. Therefore, on this 3-carbon backbone, there is a substituent that contains only 1 carbon. The syllable for a 1-carbon substituent is meth, and as a substituent on a parent hydrocarbon, we put YL at the end to make it a methyl substituent. So in our list of substituents at carbon number 2, we have a methyl group. This is the only substituent in this molecule, so this is the end of the list. Now we're ready to name the molecule. The next step is to start by listing all the substituents in alphabetical order. Good news, there's only one substituent, so we'll start by listing it, 2-methyl. We separate numbers from letters with a hyphen. Once we're done with substituents, we add the parent name to the end of the molecule name. And the parent name is propane. We're separating letters from letters, so we don't separate it with hyphens or commas. The molecule just runs together as one big long word, 2-methylpropane. Our final step is to glance through the molecule, see if there's any stereochemistry, and add any stereochemical labels to the front of the name. There's a wedge group at carbon number 2, but if you look carefully, that carbon number 2 is not a stereocenter. This isn't a video about finding or labeling stereocenters, but recall that to be a chiral center, you need 4 unique groups attached to a central sp3 hybridized carbon. Here, carbon number 2 is attached to 3 identical methyl groups. That makes it not a chiral center. We have drawn the methyl group on a wedge, indicating the 3-dimensionality of the molecule, but that does not necessarily imply that it's a chiral center. So, with no stereochemical information needed, the name of this molecule is 2-methylpropane. For our next molecule, pause the video, see if you can at least find and name the longest carbon chain. For this molecule, if we start at the top and work our way down, there are 2 4-carbon chains in this molecule. 4 is the longest carbon chain for this molecule. Step 2, we want to number this molecule to give the highest priority substituent the lowest overall number. In this molecule, we don't have a priority functional group, but the methyl group will give the lowest overall number. So we'll number it from bottom to top, giving our longest carbon chain the numbers 1 through 4. No, the longest carbon parent chain does not have to run horizontal along the page. Next, we name our parent hydrocarbon. With 4 carbons, the syllable for 4 carbons is but, so our 4-carbon parent is butane. This molecule has no unsaturation and no priority functional group, so the parent will stay butane. The next step is to list the name and location of all of the substituents in the molecule. We have 1 substituent in this molecule at carbon number 2. Sprouting off of carbon number 2 is a 1-carbon chain. Our syllable for 1 carbon is meth, so at carbon number 2, we have a methyl group. That's the end of all the substituents. Our next step is to name the molecule. We'll start with all the substituents in alphabetical order. We only have 1 substituent, so we'll start with 2-methyl, separating the number from the letter with the hyphen. At the end of our substituent, we do not include a space or a second word. We go right into the name of the parent hydrocarbon, which is butane. Our last step is always to glance through and add any stereochemical labels to the front of the molecule. In this molecule, carbon number 2 is not a chiral center. Carbon number 2 has 2 identical methyl groups attached, meaning it does not have 4 unique groups attached, and it is not a stereocenter. With no stereochemistry in this molecule, 2-methylbutane is the IUPAC name for this molecule. For our next example, see if you can find the parent hydrocarbon and number it. The first step in naming the molecule is to find the longest consecutive chain of carbon atoms. Looking at the in-the-plane atoms, we have a chain of 3 carbon atoms, but if we include the out-of-plane carbon atoms, we have a longest chain of 4 carbon atoms. 4 is our longest consecutive carbon chain. Yes, the carbon chain includes the wedge group. That's certainly an unusual presentation for an IUPAC name, but there's nothing wrong with it. Molecules are three-dimensional, and they're rotating in space all the time. For IUPAC nomenclature, what we're concerned with is finding the longest consecutive chain of carbon atoms. Next, we'll number the molecule to give the highest priority substituent the lowest overall number. We don't have any priority functional groups, so we'll give the methyl groups the lowest overall number, which means for this molecule, we'll number top to bottom. Having found the longest chain, next we name the parent of the molecule. The name for our 4-carbon parent is butane. We don't have any unsaturation or priority functional groups, so the parent is really butane. The next step is to list the substituents on the parent hydrocarbon. On carbon number 2, we have a methyl group. And on carbon 2, we have another methyl group. This molecule has 2 substituents, both methyl groups, both sprouting off of carbon number 2. Let's be really systematic when we add that to our official IUPAC name. Our IUPAC rules tell us that when we have multiple instances of the same functional group, we combine them together with a numeric modifier to tell how many of that substituent are present in the molecule. So with 2 methyl groups in the molecule, in the official name, we'll combine these together and label it as dimethyl. And when we do so in our official name, we include all the location numbers, even if the locations are the same. We would list 2,2-dimethyl. We would not just say 2-dimethyl. That doesn't make any sense. With dimethyl, I need 2 location numbers to know where both methyl groups are, even if they're both on the same carbon. Having run out of substituents, we'll add our parent name on the end, butane, and then give the molecule one last glance to see if there's any stereocenters. This molecule does not have any chiral centers. Carbon 2 has 3 identical methyl groups attached, so with no stereochemical modifiers, 2,2-dimethylbutane is the official IUPAC name for this molecule. We start with the simple examples to build a good foundation and a good intuition about naming, so that when we get to the really complicated molecules, it doesn't become harder, the process stays the same. For this next example, pause the video, see if you can find the parent hydrocarbon and number it. For this one, let's check all possible directions. Just looking at the in-the-plane molecule, there's 5 carbons in this longest chain. Just looking at the horizontal molecule, there are 6 carbons in this chain. But the longest chain of consecutive carbon atoms in this molecule starts down at the bottom and works its way back up to the top and gives us an 8-carbon chain for this molecule. Now that we've found the longest chain with 8 carbons, we need to number the molecule to give the priority functional group the lowest overall number. There are no priority functional groups in this molecule, so the methyl group will get the lowest overall number. Numbering from the left puts that methyl group at carbon number 5, and numbering from the top puts that methyl group at carbon number 4, so we'll choose to number from the top to give the methyl group the lowest overall possible number. The next step is to provide the parent name for this molecule. With 8 carbons, the parent name for the 8-carbon hydrocarbon is octane. With no unsaturation or no priority functional group, the parent name stays as the base octane. The next step is to list all the substituents and their locations. At carbon number 4, we have a methyl group. Then we put the substituents in alphabetical order, followed by the name of the parent hydrocarbon. So we'll start with 4-methyl and run that right into the parent name, octane. One last glance through the molecule to see if there's any stereocenters. And this molecule does have a chiral center. Carbon number 4 is a chiral center in this molecule. This isn't a video about how to assign carbons R or S stereochemistry, but with the hydrogen on a wedge, this stereocenter is an S stereocenter. If you'd like a refresher on R and S nomenclature, I have a video that I'll link to in the description below. This is our first molecule with stereochemical information. The stereochemistry goes out in front of the molecule in a pair of parentheses separated by a hyphen. We list the stereochemical information in numerical order. So on carbon number 2, there is an S stereocenter. 2S 4-methyl octane is the name of this molecule. Carbon number 4 is an S stereocenter, so we would name this 4S 4-methyl octane. There is a scenario where if there's only one stereochemical descriptor, you can leave off the 4 because the S has to go at the only stereocenter in the molecule. But I really prefer to leave the number in there. It makes it unambiguous where the S is, and it just gives us one set of rules for all of our names. We don't have to worry about sometimes exceptions. So I would call this molecule 4S 4-methyl octane. Now we're going to step up the ninja level a little bit. Pause the video, start with this molecule, make it as far as you can into the naming system before looking for the answer. The first step is to find the longest consecutive chain of carbon atoms. Horizontally across the molecule, there are 7 carbons. That's going to be our longest chain. Next, we number the molecule to give the highest priority substituent the lowest overall number. We have no priority substituents, so we can either number left to right or right to left to give the lowest overall set of numbers. Numbering from the left, we hit the methyl group at carbon number 2. Numbering from the right, we hit the ethyl group at carbon number 3. So to get the lowest overall set of numbers, we will number this molecule left to right, our 7 carbons in a row. The next step is to find the name of the parent hydrocarbon backbone. With 7 carbons in our longest consecutive chain, heptane is the name of our parent hydrocarbon. And with no unsaturation or priority functional group, we do not modify the heptane, and it stays heptane as our parent hydrocarbon. The next step is to list the substituents and their location numbers. At carbon 2, we have an Me group. Me is our abbreviation for methyl, so at carbon 2, we have a methyl group. Same at carbon number 3. At carbon number 3, we also have a methyl group. And at carbon number 5, the wedge group is a 2-carbon substituent. Their syllable for 2 carbons is eth, so the 2-carbon substituent at carbon number 5 will be ethyl. Recall that when we have more than one instance of the same functional group, we combine the name with a numeric modifier, and we call this a dimethyl substituent. The next step is to put all the substituents in alphabetical order, followed by the parent hydrocarbon name. And we want to be very careful here, friends, when we alphabetize these substituents. It would be very tempting to alphabetize by the E in ethyl versus the D in dimethyl and say that dimethyl comes alphabetically first. But that's not the rule. The rule is that we ignore numeric modifiers and we alphabetize based on the E in ethyl versus the M in dimethyl, and alphabetically ethyl comes first. Putting these substituents in order then, we would start with 5-ethyl, separate numbers from letters with hyphens, we would then go to 2,3-dimethyl, and we finish with the parent hydrocarbon as one long word, heptane. Notice we alphabetize by the E versus the M in dimethyl, and notice the substituents don't go in numeric order, they go in alphabetical order. Lastly, we glance through the molecule to find any stereocenters and add them to our name. There's only one stereocenter in this molecule. Did you think there were 3? That's understandable. Carbon number 2 has a methyl group and another identical methyl group in carbon number 1. Carbon number 2 is not a stereocenter. Carbon number 3 is a stereocenter, and carbon number 5 has 2 identical 2-carbon ethyl chains sprouting off of it, and so carbon number 5 is also not a stereocenter. Carbon number 3 is an R stereocenter. So at the beginning of our molecule, we can write 3R, 5-ethyl, 2,3-dimethyl heptane. Again, since there's only one piece of stereochemical information, it's acceptable to leave off the 3 and just say R, 5-ethyl, 2,3-dimethyl heptane. But again, I like to leave the number there. It makes it unambiguous. Pause the video, see how you can do with this example. The first step is to find the longest consecutive chain of carbon atoms. Here, we'll start on the left, go through the wedge to find a chain of 8 carbon atoms in this molecule. The second step is to number those carbons to give the highest priority functional group the lowest overall number. There is no high priority functional group in this molecule, so we'll look at just the hydrocarbon substituents. Regardless of which end we start with, the first substituent is at carbon 3 in both directions. Since the first substituent in ties for location number, we go to the second substituent in to give it the lowest possible number. That means we will number from right to left to give the ethyl group, in this case, the lowest possible number. The next step is to name the parent hydrocarbon. We have 8 carbons in this molecule. The parent for 8 carbons is octane, and without any unsaturation or priority functional group, it will remain octane. The next step is to look at the substituents and their locations. On carbon 3, we have a methyl group. On carbon 4, the ET is our abbreviation for the ethyl group. And on carbon 6, we have another methyl group. With 2 instances of the same substituent, we would combine these with the numeric modifier and call this a dimethyl substituent. The next step is to add the substituents in alphabetical order, followed by the name of the parent hydrocarbon. We do not alphabetize by the numeric modifier, so we'll alphabetize by the M in methyl versus the E in ethyl. Ethyl comes alphabetically first, so we'll start with 4-ethyl, followed by 3,6-dimethyl, and then as one big long word, the parent molecule octane. Finally, we glance through the molecule to see if we need to add any stereochemical descriptors. Here we really have 3 stereocenters. Carbon 3, carbon 4, and carbon 6 are all stereocenters in this molecule. Carbon 3 is an R stereocenter. Carbon 4 is an S stereocenter, and carbon 6 is an R stereocenter. Again, this isn't a video on assigning R and S labels, but you can watch that video. I have it linked in the description below. To add the stereochemical information for this molecule, we would start with 3R. We do not combine similar stereochemical labels the same way we do with substituents. We would not try and combine this as 3,6-di-R or anything like that. We simply march through the molecule in numerical order. 3R, 4S, 6R, 4-ethyl, 3,6-dimethyl octane, being sure to separate the letters from numbers with the hyphen. This one is sneaky. Pause the video, see if you can work out the parent hydrocarbon for this molecule. The first step to name a molecule with IUPAC nomenclature is to find the longest consecutive chain of carbon atoms. And it sure looks like it should be this 4-carbon chain horizontally across the molecule. But we need to recognize what the ET abbreviation here symbolizes. The ET is short for ethyl, a 2-carbon chain, so if we erase that and draw in the 2-carbon chain, now our longest hydrocarbon is 5 carbons long. I told you it was sneaky. Having found the parent hydrocarbon, we number to give the highest priority substituent the lowest overall number. This molecule has no priority substituents. Halogens, like alkyl substituents, are free substituents that are not priority, so we'll number right to left to give the first substituent the lowest possible number. The next step is to name the parent hydrocarbon. With 5 carbons in our molecule, the name for the 5-carbon hydrocarbon is pentane. We would update with unsaturation or priority functional groups, but this molecule does not have any of those. Next, we list the substituents and their location numbers. There's the halogen on carbon number 1. For the halogen groups, we take the name of the halogen and we put O at the end. So on carbon number 1, we have a bromo substituent. And on carbon number 3, we have the 1-carbon substituent, that's the methyl group. Now we're ready to put the substituents in alphabetical order, followed by the parent hydrocarbon. No tricks here. B is alphabetically before M. So we start with 1 bromo, separate letters from numbers with hyphens, 3 methyl, and finish with the parent hydrocarbon, pentane. This molecule has 1 stereocenter. Carbon number 3 is a stereocenter. Carbon number 1 is not a chiral center. It has 2 identical hydrogen groups attached. Carbon number 3 is an R stereocenter. So in the front of the molecule, we'll put 3R, 1 bromo, 3 methyl pentane. Although you could leave off the 3 and just say R, 1 bromo, 3 methyl pentane. For our next molecule, we'll follow the exact same set of steps. We'll start by finding the longest set of consecutive carbon atoms. For this molecule, we have 1 carbon here on the right and a 3-carbon chain here on the left. This 3-carbon chain will be our parent hydrocarbon. The second step is to number that parent backbone to give the highest priority group the lowest overall possible number. This group looks complicated, but it is an ether functional group. Ethers are at the same non-priority level as alkyl substituents and halogen substituents. Ethers are another of the free substituents that do not have priority in a molecule. So without a high priority functional group, we'll still number to give the ether the lowest possible number, and no matter which way we number it, it will be at carbon number 2. The next step is to name the parent of the hydrocarbon. There are 3 carbons in the longest consecutive chain. That's propane. There is no unsaturation, and ethers are not priority functional groups, so the base name stays propane. The next step is to list all the substituents and their locations. We have this ether at carbon number 2. Let's talk about how to name it. Sprouting off of the parent hydrocarbon, we have the oxygen and then 1 more carbon. A 1-carbon substituent would be a methyl group, but methyl would imply the hydrocarbon is directly attached to the parent. For an ether then, with the oxygen in place, we still use the syllable for the number of carbons, meth, but we name it as a methoxy group. Meth is our syllable for 1 carbon. Oxy is our syllable that tells us it's an ether substituent. We do not say methoxy, just the syllable for the number of carbons and the syllable to tell us that it's an ether, not a hydrocarbon substituent. Now we can construct the name. There's only the 1 substituent, so we'll start with 2-methoxy and finish with our parent, propane. Glancing through the molecule, there is no stereochemistry. Carbon number 2 has 2 identical methyl groups attached, so it is not a chiral center. 2-methoxypropane is the name for this molecule. Take a second, see what you can do with this molecule. The first step is to find the longest consecutive chain of carbon atoms. Starting with the carbon on the wedge, we can draw a chain of 7 carbon atoms in the longest consecutive chain. The next step is to number the parent hydrocarbon to give the highest priority functional group the lowest possible number. There is no high priority functional group in this molecule. Halogens, ethers, and alkyl substituents are all free substituents of no priority. If we number right to left, we don't get to the first substituent till carbon number 4, so we'll number left to right to put the first substituent at carbon number 2. The next step is to name the parent hydrocarbon. With 7 carbons in our longest consecutive chain, the parent hydrocarbon is heptane. We would update the parent hydrocarbon with unsaturation or priority functional groups, but this molecule doesn't have any, and it will stay heptane. The next step is to list the substituents and their locations in the molecule. On carbon number 2, we have the halogen. We take the halogen name and we put O on the end, so this is a bromo substituent. On carbon number 3, we have a 2-carbon substituent, that is an ethyl group. And on carbon number 4, we have an ether substituent. After the oxygen, there are 3 carbons. 3 carbons would be a propyl substituent. Recall though, there's 2 different ways we can have a 3-carbon substituent. We could have the straight chain N-propyl substituent or the forked tongue isopropyl substituent. Since these 3 carbons are all in a straight chain, it is the N-propyl substituent. So as an ether, we would drop the YL and we would name it as an N-propoxy substituent, where the OXY syllable tells us it's an ether fragment rather than a hydrocarbon fragment. Now we're ready to build the name. We list the substituents in alphabetical order, so we'll alphabetize based on the B of bromo, the E for ethyl, and the P for propoxy. We do not alphabetize by N, S, or T substituent prefixes. B comes first, so we would start with 2 bromo, then 3 ethyl, finally 4 N propoxy, and we finish with the hydrocarbon heptane. Finally, we glance through the molecule to find stereocenters. Carbon number 2, carbon number 3, and carbon number 4 are all chiral centers in this molecule. And for this molecule, it turns out they are all R stereocenters. So for our IUPAC name, we do not combine them. We would say 2R, 3R, 4R, 2-bromo, 3-ethyl, 4N-propoxy heptane. Pause the video, see if you can name this molecule. The first step is to find the longest consecutive chain of carbon atoms. If we start from the left and go our way to the right, we get 9 carbons. If we start from the left and work our way down into the substituent, that gets 8 carbons. And the same if we start to the right and go down through the substituent. So our longest chain in this molecule will be 9 horizontal carbons. The next step is to number the parent chain to give the highest priority group the lowest possible number. There is no high priority group in this molecule, so we'll number to give this substituent the lowest possible number. And whether we start from the right or the left, that group will always be at carbon number 5, so we'll just number it left to right to put that group at carbon number 5. Next, we name the parent hydrocarbon. With 9 carbons in the longest consecutive chain, the parent hydrocarbon is nonane. And with no unsaturation or priority functional group, it remains nonane. The next step is to list the substituents and their location numbers. We have this group at carbon number 5. It's our first instance of a substituent with branching of its own. We could name this as a complex substituent, but what I notice is that there's 4 total carbons in this branching substituent, so we can name it as one of the common substituents in the 4-carbon list. This is the 4-carbon substituent with the forked tongue at the end, so this is the isobutyl substituent. Since that's the only substituent, we're ready to build the name. The name will be 5-isobutyl, finishing out with the name of the parent hydrocarbon, nonane. Glancing through the molecule, there is no stereochemistry. Carbon number 5 has 2 identical butyl groups attached, and this last carbon has 2 identical methyl groups attached. We didn't have to worry about alphabetizing more than one substituent in this molecule, but had we needed to, let me remind you that we do, yes, alphabetize by the I in isobutyl. 5-isobutyl nonane is the IUPAC name for this molecule. Pause the video, see if you can name this molecule. The first step is to find the longest consecutive chain of carbon atoms. Finding all the different ways, the longest chain is going to be the one that kind of arcs up to the top and to the bottom, and this carbon chain has 9 carbons in it. The next step is to number the molecule to give the highest priority group the lowest possible number. For this molecule, we'll number right to left to give the methyl group the first lowest possible number. The next step is to name the parent hydrocarbon. With 9 carbons in the parent chain, this parent hydrocarbon is going to be nonane. The molecule has no unsaturation or priority functional group, so we do not need to update the parent name. Next, we list the substituents and their location. At carbon number 3, we have a methyl group. At carbon number 5, we have a branch substituent. We could name this as one of our complex substituents, but I noticed that it has 4 total carbons in this substituent, not including the parent carbon, and the 4-carbon substituent with 3 methyl groups sprouting off a central carbon is the tert butyl group. So on carbon number 5, we have a T-butyl substituent. That's all the substituents in the molecule. Now we're ready to alphabetize them and put them in order. For this molecule, we'll alphabetize by the M in methyl and the B in butyl. We do not alphabetize by the T, S, or N in our isomeric prefixes. B comes before M, so we'll start this name with 5-T-butyl, followed by a hyphen and 3-methyl, finishing up with our parent hydrocarbon, nonane. There are 2 stereocenters in this molecule, carbon 3 and carbon 5. Carbon 3 is an S stereocenter, and carbon 5 is an R stereocenter. So we add those at the front of the name, 3S, 5R, 5-T-butyl, 3-methyl, nonane. Notice that as the molecule becomes more complicated, the process doesn't get harder. In fact, the process gives us confidence and peace of mind that the logic that we're using is giving us the correct name, and we're not just guessing at which syllables go where. Let's end with by far the most complicated one we've seen so far. Give yourself a test, pause the video, see how you do with this very complicated name. Even though this molecule looks very complicated, we're going to follow the exact same steps in the exact same order. We'll start with finding the longest consecutive chain of carbon atoms. For this molecule, that's not going to be going up into the branch. That would only give us 9 carbons in the longest chain. Instead, the horizontal chain of carbon atoms here contains 10 carbon atoms, and that is our longest consecutive chain. The next step is to number those 10 carbons to give the highest priority functional group the lowest possible number. And here, we do have a priority functional group. The alkenes are higher priority than anything else in this molecule. So we'll number to give the alkene the lowest possible number. From the left, we get the first alkene at carbon number 2, but from the right, we get the first alkene at carbon number 1. Therefore, we'll number this molecule left to right to give the alkene the lowest possible number. The next step is to name the parent hydrocarbon. With 10 carbons in our longest consecutive chain, the 10-carbon hydrocarbon is decane. This time, we do have unsaturation in the molecule, so we're going to update the parent hydrocarbon. It's not going to be decane. We'll update the unsaturation syllable, and it will be decene. But it's not going to be decene either, is it? There are two alkenes in the molecule, so just like our other substituents, we'll combine them together with a numeric modifier, and this will be decadiene. Normally, we wouldn't include the A here, but without the A, it would be two consonant sounds next to each other, decadiene, so we add the A as a syllable modifier to give us space to say decadiene. Our next step is to list the substituents and their location numbers. At carbon 1, we have the first alkene. At carbon 5, we have a complex substituent, and we'll come back to that one in a second. At carbon 6, we have an ether. The Me stands for methyl. That's one carbon on the other side of the oxygen. So our one carbon syllable is meth, and to make sure that we know that it's an ether, we say methoxy. And at carbon 8, we have the other alkene. Let's talk now about how to name the complex substituent. For the complex substituent, we cut it off from the rest of the parent hydrocarbon, and we name it as its own little mini-molecule. We number the longest consecutive chain starting from the branching point. Here, there are 3 carbons branching off the parent hydrocarbon. At carbon 1, we have a methyl group, and at carbon 2, we have a fluoro group. With 3 carbons in the carbon chain, alphabetizing these substituents would give us 2-fluoro-1-methyl propane. But the little mini-molecule is not a mini-molecule, it's attached as a substituent on a longer chain. So instead of 2-fluoro-1-methyl propane, we change the A and E to a YL to show that it's a substituent on a longer parent hydrocarbon. And it becomes 2-fluoro-1-methyl propyl. And the whole complex substituent gets wrapped in a pair of parentheses. We're now ready to name the molecule. To alphabetize the substituents, we'll alphabetize by the M in methyl, and for complex substituents, we alphabetize by the first letter, whatever it is. F comes before M, so we start with our complex substituent. 5-2-fluoro-1-methyl propyl 6-methoxy deca 1,8-diene. 5-2-fluoro-1-methyl propyl 6-methoxy deca 1,8-diene. Now that's a name. Glancing through the molecule, there are definitely chiral centers in this molecule. But I want you to notice that there are no wedge or dash information drawn anywhere in this molecule. And without knowing which things are going towards you or away from you, we can't make it up, and so we are unable to assign RNS labels to all of those stereocenters in the molecule. At best, we could say 8E for the alkene, but we are not able to list any R or S stereocenters for any of the other positions in the molecule, and you should not make them up. If the wedges and dashes aren't given, you do not have to use the RNS labels. And that's how you name molecules with non-priority substituents. If that is actually starting to make sense, move on to the next video where we look at cyclic molecules and molecules with rings. The more you practice, the more internal it becomes, and the more automatic naming gets. I'll see you in the next video, Ninja.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.